In this video, let us discuss about internal fields in solid dielectric materials. If I take a solid dielectric material like this and I apply a electric field, an external electric field by connecting it to a battery like this and applying some voltage here, inside the dielectric there will be a electric field developed, and that is the applied electric field, which is given by the applied voltage divided by the length of the dielectric material V by L. Now we see that when the dipole is formed like this, these dipoles themselves have positive and negative charges. So if I consider one particular dipole here, this will also be influenced by the positive and negative charges of the surrounding dipoles. That means an electric field is applied on this given dielectric by the surrounding dipoles, and that I call as the electric field due to the surrounding dipoles. So this will be added to the applied electric field. So when you take the sum of the applied field and the field due to the surrounding dipoles, that is what is called as the internal field. So internal field is the applied field plus the field due to the surrounding dipoles. So this is the idea of the internal field concept. Now if I take one-dimensional array of dipoles, this is an ideal case where I take only one line of array of dipoles. The internal field in such a case is given by this formula: E applied plus 1.2 mu divided by pi epsilon naught dq. Here mu is the dipole moment of each atom and d is the interatomic distance. Now if I go to 3D, three-dimensional solid dielectric material, now the internal field in such material becomes E applied plus some constant gamma into P polarization divided by epsilon naught. Here gamma is called as the internal field constant. So this is the expression for the three-dimensional solid. Now if I take three-dimensional solid and cubic structure, a material which is having cubic crystal structure and it's a three-dimensional solid, in such a particular case we find that the internal field constant gamma becomes equal to 1 by 3. Therefore, substituting this value in the previous equation, we get internal field, which is also called as the Lorentz field. In this particular case of a cubic structure solid, the internal field is called as the Lorentz field. That is equal to the applied field plus P by 3 epsilon naught. That is, by substituting for gamma this value of 1 by 3, we get this equation. So this is the expression for the Lorentz field in the case of a 3D solid having cubic crystal structure. Now let us discuss one more concept in the dielectrics, that is called as the polarizability, denoted by the symbol alpha. So here, if I take the dipole moment of individual atom or molecule, that is mu, it is proportional to the internal field EI. So mu is proportional to internal field EI. Now I remove the proportionality, I get an equation that is mu is equal to a constant into internal field EI, and that constant is denoted by the symbol alpha here, and that represents the polarizability of the material. So here polarizability alpha represents the microscopic property of the given material. Now polarization definition, if we come back to, there are two definitions we can give for polarization. The polarization, one definition is proportional to the applied field. So if I take the polarization proportional to the applied field, I get this equation, that is P is equal to epsilon naught into epsilon r minus 1 into the applied field E. So here epsilon naught is permittivity of free space or vacuum and epsilon r is dielectric constant. So this is the definition of polarization, where we take the macroscopic view of the material. Now if I look at the another definition of polarization from the microscopic point of view, that is from the individual atom or molecules. So now polarization is defined also as the net dipole moment per volume, that is the total dipole moment divided by the volume of the material, or in other words it's equal to sigma mu divided by the volume V of the material. Or sigma mu can be written as n mu, the total number of atoms per unit volume in the material, multiplied by the dipole moment of each atom. Now according to what we said earlier, the dipole moment of each atom mu is equal to alpha into internal field. So therefore I can write this n mu as is equal to n into alpha into EI. So thus we get a second definition for polarization, that is P is equal to n alpha into EI. That is the microscopic definition of the polarization of the material. So this is the two definition for the polarization.